Yeah, so we have generated grid maps, right? So let me just go through what we have done yesterday, just to refresh. Okay, okay, yes, the one, right? Okay, so let me just delete this grid maps. Okay, we'll just generate once more. So to delete, all right. So the good thing is if you have generated or created the PDBQT files, okay, the processed one for the ligand as well as the receptor, you don't have to start from the beginning. Okay, you can just take these options, I mean the files, process files, and you can continue from here. All right, so let's create the grid files again, right? So in order to do that, you have to go to the grid option here, the third menu, and then go for macromolecules. Now previously, or in the previous session, we went through this choose option, right? But now nothing is there in our software interface, right, in the workspace. So what you can do is you have to go to grid macromolecule and you have to go for open. Okay, so you can navigate to the working folder. Since we have kept the path, the software path, so it is opening directly into the working folder, right? So you can just choose this process receptor and then click open. So there's an option here to reserve the charges. Okay, so what is saying, uh, already per atom charges, do you want to preserve these changes instead of adding Castinger? So you have to say yes. Okay, so I don't want to change any charges, whatever was there I want to keep it as such. So click OK, right? So you have defined the macromolecule. So now let's define the, okay. So you have defined the macromolecule. Now let's define or set the ligand. Okay, so for the ligand also, since it is not open in the workspace, we have to go for this open ligand option. Okay, so here is the ligand. Select this ligand in from your working folder and then click open. Right, ligand also open now. Okay, and then go to grid again. Select this grid box. Give the same coordinates that we have done yesterday. So let me just open this. Yeah. Okay, here is our coordinates, right? Minus 14.108 minus 14.108 minus 43.83. Okay, 0.83, 27.66, right? So we'll keep everything as default, and in order to save this data that we have just entered, you have to go for this file option and then go for this close saving current. Okay, then we have to save or create a parameter, grid parameter file, right? So go to output and select this save GPF, that is grid parameter file. We'll name this as grid.gpf, right? And save this. We have now saved the grid parameter file, right? Grid.gpf, right? So the next thing is to create the grid maps. So if you go here and see, there is no grid map generated, right? So we have to first generate the grid map. So for that we have to go to this run option, then select this run auto grid. Okay, here in this window you have to define the path for your autogrid4.exe file. Okay, go to this browse option and select the autogrid4.exe. okay, click open. Then again the same thing, we have to specify the grid parameter file. Okay, go to the browsed and then select this grid parameter file, okay, that we have just generated previously. Open. Now you just have to click this launch button. So it's running. It has generated the grid maps. All right. So the next thing is to generate the let me just open the workflow. Yeah, right. After generating the grid map, what we have to do is we have to uh, generate the docking parameter file. Okay, so this is the input for the final docking run. So after the final docking run, we'll be getting this doc.dlg, that is the docking log uh, file. Okay, so what we can do is we have to again go to this option after the grid parameter option. I mean the grid menu option, you have to go to this docking option. Okay, docking menu option. Same thing like what we have done in the grid map generation. We have to again tell the software or the program that this is the macromolecule that we want to dock. Okay, so in this case you will be selecting the same thing, macromolecule, since we are doing rigid uh, docking. Okay, so we are doing rigid docking for the receptor, making the ligand flexible. Okay, so we have to select this option, macromolecule, and then select this rigid file name. Okay, so we are selecting the macromolecule, so we have to click here and then go for this process CHE, that is your process file of your receptor, then click open. Same thing, we have to again select our ligand, so you have to go to this ligand option. Since the ligand is open in the workspace, we can choose this option and then select the ligand. Okay, keep everything as default and select this accept option, right? And then go for this docking and then go for this output and select the first one. Okay, so yeah, after selecting this you'll have the option for the generation of the grid docking parameter file. So I can just keep the name as doc. You can I mean make, or you can create any name and say doc.dpf and then save this. So in our working folder we must be getting yeah, doc.dpf, right? The same thing, we have to go for this run menu, and then from the run menu you have to select this second option, okay, that is run Autodoc. Fine. Again, you have to set the path, so program path where you have stored the autodoc4.exe. So we have kept it in our working folder, right? This one, autodoc4.exe. So here we have to go and select where is that autodoc4.exe. Click open and then browse again. Select the docking parameter file. Click open and then keep everything as default, and then select this launch button. So it's running. It'll take some time. So do you have any doubt from yesterday or just now in this steps that we have just done? One more thing is you should practice, okay? Don't think that after the workshop, after completing the whole workshop, I will practice. Okay? Doc.dpf step. Okay, Milan, you have to just do the same thing. So you have to, like you have done in the grid map generation. So for docking, you have to again go to this option called docking, then select your macromolecule. And since we are doing the rigid uh, rigid and the flexible ligand docking, so we have to define the macromolecule as rigid. So here we have to select our receptor molecule and then click open, right? And then again we have to define our ligand. So here you have to select the ligand with this option, then choose the option we have to select, because in the workspace the ligand is already open, right? So choose option, select your ligand, and then that's it. And you have to go to this output, okay? So you can choose this first one. So the latest the first, this Lamarckian genetic algorithm was supposed to give you a better results. So if you go to their manual, like the Autodoc manual, if you read their manual, they say that after doing multiple benchmarking and optimization, they found that Lamarckian genetic algorithm gives you the best results. Okay, so you can try all the other uh, algorithm also, but okay, anyway, let's go with their the best one. Okay, the algorithm. So you have to select this one. Once you select this option, you have the option to save the file or the input file for the next docking. So I have given the name as doc.dpf. So here you can generate the docking parameter file. When you save this, it will generate or create this doc.dpf file. Then after generating the dpf file, you can just go ahead and go to this run option, click this run autodoc, and then set the path of your docking I mean this executable file autodoc4.exe as well as your doc.dpf file. Okay, and just click the launch option. So after running this, you get a file named doc.dlg, right? So if you open this in any text editor and then scroll down till the end, so what we have to focus here is this binding energy. Okay, so you have the conformation number 8 is having the highest uh, binding energy. So it generates, it run for 10 times and generate 10 conformers. Okay, so can we generate around 100 conformers also, or 100 this docking for the single molecule? So this that you can do from here. Okay, docking option, and then in this, not in here, I think. Where is that? Okay, okay. So in the search parameter, so I missed a search parameter in the previous explanation, I think. So in the search parameter, you have to select this genetic algorithm, right? So in the genetic algorithm, there is this number of runs, genetic run. So you can increase, okay? So by default it is 10, but if you increase here 100, then it will give you 100 conformers, okay? So this you can play around, but the logic is, or the idea behind this is, if you have like in your ligand, if your ligand is like having so many rotatable bonds, okay, so many single bonds, or tell your ligand is so much flexible, okay, in that case you have to, the search for that, or you can have too many conformers that can be generated from your ligand. So there is a conformational space that you can search, okay, too large conformational space. So 10 docking 10 docking run may not be enough to uh, search the whole conformation space of your ligand. So in that case, it's always better to increase the number of GA runs, okay, depending on your rotatable bonds that are present in your ligand, okay. So this is like when you do virtual screening, we it's not possible to keep on changing the GA runs, okay. So in virtual screening, or when you do multi-ligand docking, so when you are going to take all the ligands from a database and do the screening for all the ligands against a data and against your target molecule, we would like to consider, VINA for that, okay. And then after doing docking with VINA, as well as I mean running the whole virtual screening using VINA, the top molecules, the top scoring ligands, you can do docking with VINA as well as with Autodoc, and you can compare the results. Obviously the results will be different because they use different scoring function as well as the search algorithm, okay. So now we have this results with us. So the conformation number 8 is having minus 11.46, right? And conformation number 3 is the second best scoring conformer, right? So how do we see this? How do we see this conformation or the conformers, and how do we see how they have perform, okay? So in order to see the conformations, you have to go to this analyze option, and then go to docking, and go to this open option, okay. So when you go to this open option, you have this doc.dlg file that you can open, and click open, right? Okay, and click OK. Then after this, this is the original co-crystallized ligand, okay, the conformation. But we want to see the redocking of this, right? And the eight conformer was the highest, was having the highest score, right? So how can we see that? You go to analyze again, go to conformation, and then click play. Okay, let me just hide this receptor for once. Okay, so you have the uh, experimental structure or the experimental conformation in the green color, and then the gray color is the carbon in the or the atom bonds in the this gray color is the redocking one. So we are having the first conformer, okay, and then if you click here, it's gone because from this side, from this column, it's got hide, it's got hidden, okay. So you have to select this one again to show it. Okay, this is the second redocking conformation, and if you click this play button again, you can see the third one, fourth one, fifth one, sixth one, seventh, and yeah, 8 was the highest, you know, scoring conformer, okay. So here we can see that we can see visually that okay, it's showing some kind of similar conformation as the experimental one, okay. So the dog conformation is showing some kind of similar conformation as the experimental one. So when you are doing a proper study or when you want to publish the data, you have to first, you know, uh, do a validation of your docking, okay. So validation in the sense your docking is able to, you know, I mean create the same kind of conformation as the co-crystallized ligand. So how you can do that? So whatever we have done here, the procedure, we have to just follow that, and you see we have extracted the co-crystallized ligand and then did docking again. So after doing the docking, we can see that it is showing some similar kind of uh, redocking of this co-crystallized ligand. We can see that they have some kind of similar conformation, okay. So the poses that you have got with your highest score is showing some kind of uh, similar conformation as the co-crystallized ligand. That means you are able to reproduce the experimental conformation when you are doing docking with the redocking with the co-crystallized ligand. So we can see that it is showing similar results, but we are not able to quantify it, okay. So in order to get the quantitative data, you have to do a RMSD calculation, that is root mean square deviation uh, between this co-crystallized green molecule, that is your experimental structure, and your redocking structure. If the RMSD value between the two is less than 2.5 angstrom, then they are considered to be acceptable, okay. That means your docking procedure or the docking protocol that you have followed is, you know, acceptable for docking of unknown molecules, okay. You can use the same procedure and start doing docking for another molecule other than this co-crystallized ligand, okay. So you can start doing docking for the unknown molecule that you want to try, okay. So how to proceed if you don't know the active site of, yeah, Kamlesh, yeah, we'll do this in the uh, fifth day, I think, okay. When you don't know the active site pocket, we have the tools to predict the active site pocket, and after predicting the active site pocket, we can means put our grid box in the region where it was predicted to be the active site pocket and start doing docking and see the results. Yeah, so the virtual screenings, when you say virtual screening, okay, it means like you have a large database of uh, ligand library or molecules, and you are using some tools to do screening of that molecule against some target molecule. Okay, so you can use various tools to do that. You can use 2D similarity search, then you can use pharmacophore also, and you can also use 3D QSR based screening. Okay, but you can also use docking for screening the large databases. So for this, I'm just showing you one single molecule. Okay, so in Autodoc 4, virtual screening can be done. Okay, you can use multiple ligands and large databases to screen, but it takes time and you need to do lots of processing. Okay, so it's always better to use Autodoc Vina. So we will be using Autodoc Vina for virtual screening. Okay, first we'll try with the single molecule using Vina, and then we have this software called Pyrex, where it has made it so easy for doing virtual screening using Vina. Okay, so Pyrex is just an interface. They are also using Vina in the background. So I will show you how to do virtual screening using Pyrex. Okay, after that we are going to use an automated script using Python. Okay, to do ligand preparation and then virtual screening and extracting of this high scoring the top scoring ligand molecule against your target. Okay, so don't worry, we'll cover all those things that you are asking. So now what we can do is we have to calculate, so we have to calculate the RMSD value. So in any docking, it is important to calculate the RMSD value, okay, to validate your docking protocol. So just think of this co-crystallized ligand. Okay, we are just following the docking where you have the co-crystallized ligand. Okay, so for uh, for the target which does not have co-crystallized ligand, we have to follow different method. Okay, so for now you just consider that you are having a your target is having a co-crystallized ligand, and now you want to validate the docking protocol. So you have done the redocking of the co-crystallized ligand, and you want to see the RMSD value between the experimental conformation and your redocking conformation. Okay, so if the conformation or the redocking and the the original conformation, if their RMSD value is less than 2.5 angstrom, then you can use that protocol, or in a sense you have validated the docking protocol. Okay, so now you can use another molecule to do docking. So in order to do that, see here you have this DLG file, but there is no other files, okay, separate file for your docked conformations. So in order to generate those files, what you can do is you can just click this ampersand. Okay, right, so you can play around with this all this option available here. Okay, and then in order to create the files, we have 10 conformers, so only this DLG file is present here. So in order to extract the 10 conformers from this DLG file, what you can do is you can click this one. Okay, the write all option. So when you click this write all option, it will generate all the, or it will extract all the conformers from the DLG file. Okay, so it started from 0. So our the best docking conformers is the 9th one, right? Okay, let me just see. Okay, so 8, right? So it will be the seventh one, correct? It started from 0, so it was the highest scoring conformers was 8, right? So it is starting from 1, so it is the 8th one, right? So in our case, it is the conformer is when they separated the conformers from the DLG file, it started from 0, so it will be the 7th conformer which is having the highest score. Okay, so what we can do is we can take this conformer, the highest scoring conformer, and your ligand, right? So ligand, that is your original experimental conformation, and see the RMSD between these two. Okay, so in order to calculate the RMSD between these two, we have a, so we can do in Mastro, but uh, it it requires license to calculate that. So let's just go for an open source tool called doc RMSD. Okay, so if you go to this doc RMSD website, now you see they only accept the input files, that is your dot conformation and your original conformation in mol2 format. Okay, so but in your case, in our case, we have this in PDBQT format, right? So we need to change the format. Okay, so I've given you the link for OpenBabel to install. So when you install OpenBabel, you will get a interface or app, something like this. Okay, open this. This is graphical user interface. Now here, okay, already the input format is PDBQT, right? So we need the PDBQT as input because our files are in PDBQT format. So let's first change the ligand.pdbqt, the original one, right? The reference or the co-crystallized ligand. So can go to this. Let's go to our working folder and then select the experimental structure, right? Then click open. Fine. And this is your output. Okay, so what format do you want as in the output? You want in the mol2 format. So many formats are there, so you have to select the mol2 format here. Okay, mol2 format, and then you have to define the path where you want to store the output file. Okay, so for that you have to go to this browse option, and then your docking file is there, and you say ligand dot mol2. Okay, and click the saved button, and then finally click this convert button. Okay, when you click this convert button, one molecule's got converted, and here you will get the converted molecule ligand.mol2. All right, the same thing we have to do for the conformation, the seventh conformation, the highest scoring molecule or the highest scoring the conformer. So the input format is in PDBQT, and then we have to select this conformer, open. The same thing, we have to select this output format and then tell where we want to store it. So I'll say that docked, okay, 8, okay, conformer number 8, right, mol2, and then again click this convert button. So one molecule got converted again, so we got the reference ligand as well as the docked confirmation, right? So now let's go back to the website called doc RMST. So I can select now uh, the ligands, right? So for selecting, you can keep any of the uh, select original here, or you can select the original here also, same thing. So you can just choose one of the files. I'll just go and select the original one first, and then upload here the docked one. Okay, docked 8.mol2. Click open. Here I uploaded. Okay, here I uploaded the original file or the experimental confirmation, and here I uploaded the docked confirmation. So don't need to do anything, you just have to click the run doc RMST option. So it's calculate the RMST value and it is 0.636 angstrom. Okay, that means your docking that you have done is pretty good, and you can just use the same protocol to dock other molecules. Yes, are you following this? Right? So let's do a docking of a new molecule. Okay, so renan cantin Q. Okay, so just a random molecule I picked up, and we want to see how it docks. Okay, or otherwise let me just show you interaction first. So open this Maestro. I have sent you the link for installing Maestro. Download and install it. Let's see the interaction, how the interaction is between the docked uh, conformer and the original ligand, and we can also see how the unknown molecule, unknown in the sense we don't know if it is having activity or not, right? So this is a natural product molecule. I've just taken from one database and kept it here for showing you as an example. Okay, so this is Maestro interface. So again you have to go to file and then go for change working directory. So I want to keep the path of this software to my working directory, okay, or my working folder. So to D drive, then go for docking, and I select this as my working directory. Now if I want to open a file, you have to go to this file option and then import structure. Okay, so here we can just select. Another thing is, it doesn't, the Maestro doesn't accept the PDBQT format. Okay, so only the process one is there, only containing only the receptor. Where is that? This one. But I cannot import this because it is in PDBQT format. So you just can take this PDB one, the clean, this contain only the receptor and the ligand, right? So we can take this one and then click open, import. So it contains the receptor and the ligand, right? So let's process this. It doesn't contain hydrogen atoms. So if you want to see hydrogen bond or any other interaction, uh, it won't be able to show the interaction properly. So we have to process this. For processing, you have to go to this protein preparation menu. So in this window, you have many options to prepare the receptor, but let's uncheck this because it all requires license. So we don't have the license. So okay, this one I can just uncheck this, go to more option, again uncheck this one, because again Epic is, you should have license for Epic also. So if you keep Epic, if you choose this option, it will create error in the later step. Okay, anyway, just keep everything as default. Right, and then click this run button. Complaints you are asking, like RMSD. Yeah, yes. If you see their citing, okay, many publication cites their paper. Okay, so Kamlesh, you see whatever we are showing you here, okay, the same step you can follow, and you can, see how people are publishing using, I mean, the format, how you can write for publication. Okay, in the material and method, whatever we have done, you have to compress and write it. Okay, so the same procedure you can use that what we are doing here and go for publication. So once you validate your docking protocol and it is good, then you are good to go for docking another unknown molecules. And I will also show you in the last session how you can generate a good quality, or you know uh, good looking, I can say, like presentable, publication ready images. Okay, so don't worry, if you're looking for publication, then the steps that we are following, you can use the same procedure and go for publication. All right, so we have prepared the receptor and the ligand, but since the ligand is inside this active site pocket and we want to see our newly docked conformers inside this pocket, we need to extract this or remove this ligand. Okay, so what you can do is you can do right click here and then say split, and then select this third option. Okay, into ligands, water and others. So this was our previous structure. Now it got splitted. You have the ligand alone and the receptor alone. Fine. So now you can import our dock molecule. So we have mol2, right? This one. So we have the mol2. Click open. Click import. Here is our mol2 format of the dock molecule, and we can show in the, so see in the workspace, if I select this one only, it shows only the ligand. So in order to show the receptor also together, you have to press the control button. Okay, when you press the control button and click here, then it will show you the receptor also. Okay, now it is not, I mean, I can't see where is the ligand and where is the active site pocket. Okay, so you can click this L option, that is the ligand option. Click here, it will automatically zoom in. Okay, still now I'm not clearly see. So here is the ligand, but I'm not seeing it clearly. So what you can do is you can, okay, this is the one, right? So docking series something November is the name, and here there is a paint option. Okay, so in the paint option you can change the style, okay, or representation. So now I can see the ligand properly, and if we want to see the interaction, 2D interaction, we have to go to this ligand interaction option. Okay, see, so it has interaction with the tryptophan 286, phenylalanine 295, one hydrogen bond. This is a pi-pi interaction, another pi-pi interaction with tryptophan 86. So this is the docked conformation. So what about the original conformation, right? Or the original ligand. So this is the original ligand, prepared ligand.pdb, right? So now I'm showing with the prepared ligand and the protein, okay, on the and the receptor. So if I go to this ligand interaction option, so it is showing exactly the same thing. 3 interaction, 2 is pi-pi interaction with tryptophan 286, tryptophan 86, and phenylalanine 295. That means your redocking of the co-crystallized or the experimental structure, uh, it's able to produce the similar interaction as the original or the experimental ligand. Okay, fine. So I will show you how to make a 3D interaction diagram or the figures, okay, or images properly, okay, in the last session. So I just wanted to show you the interaction, 2D interaction. That's why I was using Maestro. So let's go back to that, this natural product. So let's dock this natural product, okay? So let me just copy this, otherwise we'll get messy here. So I'll name this into dock king 2, right? So what we need is, we have already processed the receptor. We need the receptor processed, and we need these 2 files, right? That's it, I think. And then this information, right? Grid information. All right. So let me just restart this. Are you guys following, or you got lost? Great, great. So let's restart this. So what we are doing now is, we have done redocking of the co-crystallized ligand, and now we got around 0.6 uh, angstrom, that is in RMSD value, between the co-crystallized experimental conformer and the redock conformer. That means our docking protocol that we have followed is in the acceptable range, right? So let's try with another molecule, which is, not the active molecule or the co-crystallized molecule. Okay, so let's start. We already have the prepared structure for the receptor, but we have to prepare the ligand, right? So for preparing the ligand, what we can do is we have to add hydrogen atoms. Okay, we need the polar hydrogen. You see, we in the first previous step we went from this ligand option. Okay, I went from this option because we don't have to add polar hydrogen in the donepezil or the drug molecule, because uh, in donepezil there was no polar hydrogen to be added. But in this case, in this new molecule, we need to add polar hydrogen because there is position for adding polar hydrogen. So in order to add polar hydrogen, what you can do is you can go for this file option, read molecule. Okay, we need to change the this working directory, right? So we have changed into docking 2. So we need to set the path to docking 2, right? Docking 2. Like this as default. Now let's try to open it again. Now it's opening in our docking 2 folder. So let's open this. Okay, already the hydrogen atoms are added, but all the non-polar also is added. So what you can do is you can go to edit hydrogens and you say merge non-polar. Okay, so all the non-polar hydrogen atoms are removed and only the polar hydrogen is added here. Then you can go to this ligand option, input, and then you have to go for this choose option. Okay, choose this and select. So charges is adding automatically, and it has 9 rotatable bonds, right? That means 9 torsion angle option you can set. Anyways, let's click OK. So we have processed the ligand, but we haven't saved it in the PDBQT format. So let's save this into PDBQT format, right? Give the same name, save. Let's create the grid file for this, or grid parameter file, macromolecule. Since it is not there, we have to go to this open option, click the macromolecule in PDBQT format. So already has partial charges. Do you want to preserve these changes instead of adding? Yeah, I want to preserve this, right? And click OK. Macromolecule is done. We have to set the ligand again. Go for choose ligand because already open here. Choose the ligand here, right? Then grid, we have to set the grid box. This one, yeah. So minus 14.108 minus 43.83 and 27.66. Okay, everything as default, and save this option, save this data. Okay, go to grid again, output, save GPF. Okay, let me name this as grid.gpf, right? I have to run this. select the GPF file and then launch. So it's running. So it's generated the grid map files. So let's do calculation for docking again. Macromolecule, set rigid file name, choose the receptor file, right? Docking ligand, choose the ligand here, ligand, accept, docking, which search parameter you are using, genetic algorithm. Let's increase this, okay? Let's see. I'll keep it 15, right? Let's see if 15 conformers are generated or not in the final docking. Accept, docking, I'll go for output, the first one, and then I'll say docked dot dpf. Saved. Same thing, we have to go for this run option, run autodock, select the .exe file, autodock4.exe, and then dock dpf file, and click launch. So in this case, should we be doing the RMSD calculation? Anyone? Can anyone answer me? Yes? Anyone? After this, as in the previous step, should we be doing the RMSD calculation? Jara is saying yes. Any other? So we won't be doing the RMSD calculation because this the RMSD calculation we have done before, because we want to see if your redocking of the experimental structure, okay, redocking of the experimental structure is doing your docking is able to reproduce the same conformation or not, just to see if your docking is, working or not. Okay, but if you are doing this docking with another molecule, so let me just show you here. This structure is different from the original structure, okay, the original drug molecule. So how can you calculate the RMSD value between these two? Okay, so atoms are different. So RMSD means you can calculate for the whole atoms or you can calculate for the heavy atoms, but all these are different from the original one, so you cannot get the RMSD value for this. But anyway, the idea is to see if your redocking is able to reproduce the same or similar conformation as the experimental conformation. Okay, so once you have done the validation of your docking, you don't need to calculate the RMSD for the unknown molecules. So what you can do is you can compare the scores. So in your redocking of the drug molecule, what was the score? Doc.dlg, where is that? So it was 11 point minus 11.46. Okay, if your unknown molecule docking with your unknown molecule is comparable or better than this uh, docking score of your drug molecule, then yeah, you can consider this newly docked molecule for further studies. Okay, or if they have similar kind of interaction at the active site pocket. So if you are particularly looking for molecules which have similar interaction as the drug molecule at the active site pocket, then you can consider your newly docked molecule or the unknown molecule if this molecule is having high binding affinity as the drug molecule and also showing similar kind of interaction as the drug molecule. Okay. Yeah, good question, Jara. So you can do RMSD for all the generated molecules, but what we'll consider is the highest scoring docked conformer. Okay, but there is no guarantee that the highest scoring molecule will be the active conformer. Okay, that will represent the active conformer. So you can always do RMSD for all the other conformer and see which one is having the lowest one. Okay, but generally when we try and do docking and see with all the other conformers the RMSD value between them and the original crystal structure, we always find that uh, the the highest scoring gives you the best RMSD value, but it is not always the case. So you can keep on testing. Okay, so docking is done. Let's go to doc 2 and the DLG file is there. Let's see the score. Hopefully it's also having nice score. Okay, conformer number 1 is showing better than the drug molecule. Okay, minus 11.58. All right, so let's see what is the interaction. So for to see the interaction, what you can do is you can open the DLG file. You can go to this conformation and then play, right? Go to this ampersand and click this write all. So conformation number 0 will be the highest dot conformation. So let's convert this into Mol2 format so that we can import in Mastro, right, to see the interaction. PDBQT, then go to this first, no, doc2, first one, open, and then change this to something else. I'll say make Q, that is docked, right, to, and go to convert. So I should be getting, yeah, Rinakentin q dot mol2, right? So let's import this in Maestro. Click open, import, and let's show only the this docked molecule with the protein, right? And let's see the 2D ligand interaction. Okay, it's showing tryptophan 286 and phenylalanine 295, but the tryptophan 86 is missing. Okay, the interaction between tryptophan 86 is missing, but we still get two interaction. Okay, and even this phenylalanine has uh, two double bonds, two hydrogen bonds. Okay, so this is how you can analyze, and if you are not looking for molecule which have different interaction than your drug molecule, you can disregard this, or you can just remove this from your study. Or otherwise, if you are just looking for uh, docking score greater than or equal to your drug molecule, then you can keep this also. But the thing is, you see, there are 15, right? 15 conformers. Out of this 15 conformer, though, see, they are having different scoring scores. Okay, but these are not uh, that much different. Okay, from here 11 to 58, right? 11.58 to 11.04. Okay, so you can see the conformation of this four and see if the conformation can give you a similar interaction as the drug molecule. Okay, anyway, this is for just looking for one molecule at a time for the highest uh, I mean, when you do virtual screening for those highest scoring molecules. Okay, so in the virtual screening or multiple ligand docking, you cannot keep on looking like this. So based on the score only, you have to uh, list it out according to the score, and you can do further studies for the highest scoring molecule. So next time we'll be doing multiple ligand docking using Veena, and also the complete automation using the Python script. All right, any doubt you have, you can ask me now. So no one has, everyone is able to follow. Great, great. So I'll be giving you the these files. Okay, you try to practice it. Okay, I'll give you the file for these unknown molecules, whatever the results I've got from here, and also the your original structure or the molecule. Okay, the drug molecule also. So you need to practice. Okay, so when you practice alone, you'll get so many errors. So if you are
Sir,
doing for the first time, yeah, go ahead.
sir, I have a doubt, sir. Sir, I could not view the master viewer link that you have sent us day before yesterday, sir. Sir,
No, I have sent you today, I think.
you have sent the link for the master viewer, but it is not opening for me. What should I do, sir?
It should be opening. I think I have kept the option that with anyone with that link they can open. So I haven't given any restriction there.
Sir,
Try it once again. I haven't given any restriction to the file. So anyone with the link they can open and download.
okay, sir, you have sent the link, but it is not opening for me.
I've sent an
Yesterday,
email
yeah,
today
email, sir.
itself. Not day before, not day before yesterday. I just sent
I
today
think
only.
25th, sir. 25th,
No, no,
sir.
no. You see for today.
Okay, okay, sir.
Okay?
Okay, sir. Thank you, sir. Definitely.
Okay. So Milan is asking me why there are so many less drugs with less success rate of Alzheimer's disease. Yeah, that we have to see. So not only for Alzheimer's disease, you see, drug when you do drug discovery, most of the drug fails at the this I mean this clinical trial phase. Okay, so drug maybe whatever drug you may be getting nice results in the in vitro kind of testing, but when you applied it in the real scenario, it doesn't work. So most of the time it due to the ADMET properties. Okay. All right, then let's meet up tomorrow. So tomorrow we'll be doing multiple ligand docking with Vina first, and then Pyrex, and if possible, we'll complete this thing also, automation of uh, the complete docking procedure. Okay. So there is one uh, program called Anaconda. So please download and install Anaconda. Okay, it's also a straightforward installation. You have to just go for next, 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 and then it will download. Okay. Okay, we'll see tomorrow. Okay, bye bye.